Hello, physical science. I come to you in my dog walking clothes with my dog walking hair because I wanted to get a little video to you, just a little something to bridge the gap between our first class and this next class coming up on Thursday. I apologize for it not being here last week instead of class, but it was a crazy week. I think we all had one. So here I am today. We're going to talk about forces and about forces being in balance. We're going to talk a little more about inertia. We're going to discuss weight. We've got some good topics. I've included a couple videos for you in the email I'm sending out that have to do with weight and inertia. And today we're going to talk a little more about that and some other things. So let's get to it. I have up here a picture of a little stick person on the earth and a little stick person on the moon. Now, we talked about inertia in class, first class that we had a week and a half ago. And when we discussed inertia, the tendency of an object to resist change. If it's moving, it wants to keep moving. And if it's still, it wants to stay still. Or if it's at rest, it wants to stay at rest. That's another way to say that. We discussed how that had to do with the mass of the object. How mass was a way that we could use to compare the inertias of different things. So I think the example we used in class was a mouse and a truck. And the mouse had less inertia than the truck. But some of you said that if we could push the truck, if we tried to push it, we would be able to push it as long as it was in the right gear. And that's what one of those videos addressed, is what's going on there. The weight of the truck makes it more challenging to push than the mouse, but the mass is what really determines the inertia. So I wanted to talk about these two people on Earth and Moon to highlight some of the differences between mass and weight. So the mass of the object, how much matter is in the object, how much stuff it's made of. Like if we added up the masses of all our carbon and hydrogen and oxygen and phosphorus and sodium and calcium ions and atoms, we would be able to get the total mass of our bodies. And we can also just step on a scale and we can see what that is. But the mass is how much matter that something has in it. So if our person on Earth has a mass of 90 kilograms, would that mass be any different if that person were on the moon? Would their mass change based on their location? And you're probably saying no, it would not change. And maybe you've read the chapter and that's why you know they would not change. But the mass will stay constant. It doesn't matter whether you're on the Earth or the moon or Jupiter or Mars, or if you're in some sort of orbiting space station vehicle that's going around the Earth at 15,000 miles an hour, your mass is always going to be the exact same, as long as you're not losing weight by throwing up in outer space or gaining weight by eating the moon that's made of cheese. It's not really made of cheese. Sorry. Okay, so mass is constant. Now, weight. What is weight? We talk about losing weight all the time, don't we? We hear commercials about losing weight, talk about unexpected weight gain from certain drug commercials you'll hear about on TV. So weight is different from mass. They are not the same thing. Weight is dependent on the gravity. So I'm going to just write up here that weight changes. Hold on. Someone's at the door. Sorry about that. FedEx delivery. Okay, life at home. I'm in my son's room. This is where I do tutoring. So that's why I have like gymnastics medals behind me and pictures and stickers all over the place. Anyway, it has the best lighting and it's probably even still not that good. So I apologize if it's hard to see me. All right, I was writing up here that weight changes. Weight changes and it depends on gravity. So the weight of my little person on the Earth is actually directed down towards the center of the Earth because it's coming from the gravitational field of the Earth. Now that sounds a little complicated, but our weight is coming from the attraction between the Earth in our bodies. And that attraction is always directed towards the center. And we represent it with an arrow. We're going to call that a vector. And you're going to see a lot of vectors, a lot of arrows in this chapter. So the weight of our person is directed downward. And it's measured in a unit called newtons. I know that we use pounds here in America. But when we do science weight, we're going to use newtons instead. And we're going to use gravity to calculate that. I'll show you in just a second. That says 900 newtons, by the way. But that would be his weight here on Earth. On the moon, he would also have weight, right? The moon does have gravity. Some people get confused because they look at those astronaut videos and they're like jumping in the air really high. The moon just has less gravity because it's a smaller orbiting body. It has 1/6 the gravity of Earth. So you would weigh 1/6 of what you weigh here. So if whatever you weigh here, just divide it by 6, and that would be your weight on the moon. So the moon, your weight would be less, and I could calculate that, but of course I didn't set my calculator here. So it would be 900 divided by 6. And then what about out here in space? We're going to talk about this a little bit, but technically this is an area we define as being weightless. Now we'll talk more about why you're weightless. It's not that there's no gravity out here. There's still gravity. It has to do with your motion. And if you think about how you feel when you're on rides at Six Flags, when you're falling through the air, coming off the roller coaster hill, whatnot, that kind of thing, that's the same feeling they have in space, that weightless feeling. And it's really a falling kind of feeling because they're flying around the Earth at such a high rate of speed. So these are the two big things I want you to remember, that mass is constant no matter where you are in the universe, and that weight changes. It's not the same as mass, it's related to mass, and I'll give you the relationship in a second, but it depends on gravity, so the weight's going to change as the gravity changes. So the relationship between mass and weight, I'm going to go ahead and I don't think I need to keep up my space station guy or my moon guy anymore. The relationship between mass and weight is that 1 kilogram of mass is equal to 9.8 newtons of weight. And that has to do with gravity. Now, I didn't use 9.8. I actually rounded it and used 10 here because that's kind of common to do. But 10 newtons is really our sort of the rounded estimate that we use, because it's a lot easier to do math with 10 than it is with 9.8. But that's a relationship between mass and weight. I don't think there's any math problems in your chapter that you have to do with that. I think everything in the chapter that has to do with mass, weight, and inertia is all conceptual. So you should be able to make it through most of those problems in week 2. I'm going to talk about a couple more things though that have to do with forces in particular. I want to look at this guy here on the Earth, and I want to look at how he's got a force pulling him downward. Well, what Galileo explained is that if you have a force applied to you in any direction, that you're not going to be able to have your inertia state continue. If you're at rest and there's a force applied to you, you're going to accelerate. And if you're in motion and there's a force applied to you, you're going to also accelerate, which might mean you speed up or it might mean you slow down. But this guy who's sitting here on the surface of the Earth should technically be accelerating, and he should accelerate in the direction of that arrow, which means he should be crashing into the Earth, busting a hole right through it. But that's not happening, right? Why is that not happening? Is there another force that's acting on him that's keeping him from running right into the center of the Earth? I'll let you think about it a second. There is a force that's coming up on his feet from the Earth. And that force is directed upward. It's equal and opposite, and it's a support force. So he actually has two forces acting on him. He has a force downward, his weight, and then he has a force upward from the Earth that's acting on him and that's supporting his weight. If he were standing on a table made out of paper towels, that would not give him very much support. So in that case, the support force would be too small and he would fall through the table of paper towels. If he were standing up in a building on a concrete floor, that would give him plenty of support force probably. But as long as the support force going up is equal to the weight going down, then he will be in a state of equilibrium. And equilibrium is a very fancy long science word, but it just means that everything that's acting on him is balanced out. I'm going to draw another picture of equilibrium and just talk about that a little bit further. If I can erase all this dry eraser on the board. Okay. All right, I have a lovely, I should probably make my plant actually touch. All right, it's a beautiful potted plant, right? Let me make it actually come in contact with the table, because we are talking about forces in motion, and I do not want to imply that there's some kind of levitation going on in physics. I mean, there can be, but there's always going to be forces at work on it. So we have a potted plant. It's sitting on a table, and it is currently at rest. It is not moving. And because it's not moving, and there's no motion, it's not going left, right, it's not going up, down, that means that it is in a state of equilibrium. In a state of equilibrium, that means that you have a net force of 0 acting on your object. And I'm going to draw a funny thing. This is a sigma, and mine might look different from the book because I can't write as neat as the book. It's like a really jaggedy backwards 3, but it's called a sigma. You can also write it this way, which a lot of my physical science students prefer, to say that the net force is 0. Now, it doesn't mean that there's no forces acting on the potted plant. And do the forces on the potted plant look like something we've already done with the little dude standing on the surface of the earth? Yes, they do. So we have acting on this plant a force downward, and that's the weight of the potted plant, and it's acting towards the center of the earth. So that's one force acting on the plant, and if the plant's sitting still, there has to be an equal and opposite force acting on the plant. So that means there's going to be a normal force. Now, I've just called it a normal force, and I'm going to label it with an N. You're going to be like, but you just call that a support force. So let me erase some of the table legs because that's kind of an excessively tall table. So a normal force is another fancy physics way of saying support force. Here's why it's called a normal force. If you've had math classes, you might have heard of this. I know you've had math classes. If you have had a math class like geometry, then you've probably heard of a normal. It's a line that's perpendicular to another line. So the normal implies, I can't fit this on here, that it's perpendicular to the surface. So the surface that the thing's sitting on has a vector coming out of it. It's perpendicular, and that's why it's called a normal force. Not because it's not, you know, it's not normal, but it's normal. Did that make sense? Okay, great. So the net force on this plant on the table is 0. If the table was made of rotted wood and it couldn't support the plant and this normal force wasn't quite as big as the weight, then it would crash through the table. But there's never going to be a case where the normal force is larger than the weight, because then the plant would like go up into the air, which isn't a thing that happens unless there's something up here creating some kind of force that attracts it, like with magnetism. So this means 0 net force. This means 0 net force. And what that means is it doesn't matter if there's 14 forces acting on an object, that they all balance out, cancel out, and then when you add them up, they equal 0. We don't have to worry about 14 forces. We're only going to be doing a couple. So let's do another example where we have something that's got a 0 net force, but is, I'm trying to think, no, let's just do some hanging stuff, because I know you guys, I want to be sure to cover that, because y'all have some stuff in your book, some questions about guys on scaffolding, walking around, and I'm going to give you another little practice page on Thursday when we see each other. Okay, so we have this cute little guy, and he's on some kind of scaffolding. He's got cables that come attached to this thing. His feet actually touch the ground, because apparently I am unable to draw somebody actually at rest on the ground. So let's throw some vectors up here. Let's say that the scaffolding has a weight of 500 newtons. And let's say that this guy here has a weight of 1,000 newtons. I wrote those kind of small. That says 500 newtons for the scaffolding, and there's another vector pointing down that says 1,000 newtons. So that means we have a total force downward of 1,500 newtons. Now, if he's right in the center of these two support cables, this is not one where we have a support force coming up from a surface like we did with the plant and the person standing on Earth. This is one where this guy is on a scaffolding, and that scaffolding is hanging from some kind of ceiling or something. You can think of it like a swing from a branch of a tree, however you want to think about it. But what happens here is that you have, I'll use a different color, you have forces that are going up, and they're going up along the cables. Those forces going up have to add up to equal all the forces going down, because this person's not moving. We need them to express that they're in equilibrium. We need to express that they have a net force of 0. So if we have 1,500 newtons of force downward, that means we're going to have to add up to have 1,500 newtons of force upward, because we want the net force to equal 0. So if we need 1,500 newtons up, we don't want to put 1,500 on one side and 0 on the other, because this guy is right in the center. We're just going to half it. We're going to do 750 on one side, and then we're going to do 750 newtons on the other. 750 plus 750 is 1,500, and that will match the 1,500 that are pointed down, and that will mean that we have a net force of 0. So in your book, you've got some questions like this, and then the guy might move to the left or to the right. If he slides over to one side or the other, he still weighs the same amount, but now he's going to go over here, and we're going to find out that this side ends up having a bigger weight. So let's say that he's got now 1,100 newtons on this side. That should be like a number. There we go. So when he scoots over to this side, he lost his arms. Did you notice that? Let's draw some arms on there. Okay. So when he scooted to this side, now it changed it. It's not going to be split up half like it was before. It's going to change, and there's going to be more tension or more force on this one than there is on this one. So the 1,100 newtons reflects that. How much is there on this one? If there's 1,100 newtons upward here, how much will be over here? We got to just say 1,500 minus 1,100. And then we can figure out that there will be 400 newtons on the right cable, whereas there's 1,100 newtons on the left. Now when we think about what this force is, like it's going upward, but when you're sitting on a scaffolding or a swing, it seems like that's getting yanked downward, right? This is actually a type of force called a tension. I haven't officially defined forces yet, because it really is in the next chapter, but a force is generally a push or a pull that can start or stop or change the direction of something. And a force acts all in one direction. So if I take my jar here with pins in it and I apply a force to the right, all that force is acting in the same direction. So that's why it's called a force. This is a little bit different with these cables or anything that's hanging because the force isn't all going in the same direction. If you looked at it up at the top, it would look like it was pulling upward. And if you look at the bottom right by the scaffolding, it would look like it's pulling down. So a tension is like a pulling apart when you take something and you tug on either end. And that force is pulling apart or going in different directions. So it's called tension. I think it's pretty self-explanatory. I just wanted you to know on the worksheet you do this week and that I give you Thursday, and on the homework problems when it says like T1, T2, that's referring to the tension that's in these two cords. Okay, I think that is all I'm going to talk about with regards to things staying still. These are examples, by the way, of static equilibrium, meaning that they're still, they're not moving. So the plant is not moving. This guy on the scaffolding, I know he's shifted over, but in general, he's not moving up or down. So all the forces are balanced. The last thing I want to talk about is some things that might be moving that are also in equilibrium, but we call it a dynamic equilibrium. Okay, let me erase this. An eraser, and I'm only ever reminded of that when I'm erasing. Okay, let's discuss. I'm actually going to use a different color. There's a large box, and there is a person that's pushing the box, and they are applying a force to the box. I'll use my black one now. Well, first of all, before we start sliding this box across our floor, does the box have weight? It does. This box has a mass, and if the box has a mass, then we know that it's also got weight acting downward. Is the box plummeting into the center of the earth? It does not appear to be. And that means that there has to be an equal and opposite force acting upward on the box. So it's going to have a support force acting on it too. I'm just going to draw it up here on top of the box. So we have our weight, and remember this is our normal, or also called support force. Now let's talk about him sliding this box over, because I want to keep this box nice and steady. I don't want him to be running with it after a few seconds. I want him to just push it nice and steady, like everybody likes to push a box, right? So he's going to apply a force over to the right because he's pushing on it. Now, if we look at this picture, does this look like a picture where all the forces are balanced out to zero? It doesn't quite look that way, because this force and this force are equal and opposite. So all the forces in the direction, vertical direction, are canceled. So there's no force. It's not moving up or down. It's moving to the right, but there's a push to the right and there's nothing happening to the left. Is that an accurate description of what's going on with this box right now? If he were pushing that box on an ice rink, it might be pretty accurate. But if he were pushing that box across carpet or across a wood floor, or heaven forbid, a gravel parking lot of some kind, there would be something going on that would be fighting against that push. What is that something called? I'm going to use a little curly F, and I'm going to tell you that that force is a friction force. So the force of friction is going to act in the opposite direction of motion. And in many cases, the frictional force is going to be equal and opposite to the pushing force. If that is the case, the box could either be still or it could be moving at a constant velocity. Now, I just threw a word out there like you guys had heard it before, and you probably have heard the word velocity, but we haven't talked about velocity in physics yet, so don't freak out. We're going to talk about it on Thursday. I just want to introduce to you the idea that an object that has all the forces balanced, so if this is equal to that and this is equal to that, then we know that we have a net force that is equal to 0 all the way around, both vertically and horizontally. That does not mean that this is sitting still though. That's kind of the interesting part. I think it's pretty cool. This box could be sliding along at 1 meter per second or 2 meters per second or 100 meters per second, or it could be sitting still and all these forces would still be true about it. We're going to get to talk about that some more, not only next week when we see each other, but also in the weeks to come when we talk about forces. But I just wanted to bring up the idea that a net force of 0 doesn't mean that it has to be at rest. It can also be moving, but it does mean that it's not accelerating. I'm not going to write that down yet because we're going to talk about that more in class. And I'm pretty sure that's all I wanted to cover. So enjoy yourselves. Y'all should be able to answer the week 2 questions in chapter 1. So please take a look at them before class. That way you can ask me questions if you have any. But they deal with the difference between mass and weight. They talk about the relationship between mass and inertia. They talk about the net force stuff we did with things hanging. And then a little bit about friction. So give those a try. And I've got another worksheet for you, and then we're going to talk more about speed and velocity and acceleration in our class on Thursday, and we'll actually finish up chapter 1 on Thursday when I see you. All right, take it easy.